Tonight on Nova, supernova. A star blows itself apart in the most violent event in the universe.
It's just a great thing. You sort of hope all your life, really, that you're going to get to see something like this.
Well, I almost fell over.
I remember walking around for about a week, and everyone I would see, I'd say, boom!
Astronomers the world over scramble to uncover the mystery behind the death of a star. February 23rd, 1987, the Las Campanas Observatory in a remote region of north-central Chile. Soon after sunset, Oscar Duhalde arrived at the 40-inch telescope to start work. Oscar is the telescope's night operator, and his shift began routinely enough. He first checked the controls and the observing schedule before choosing some appropriate music by which to gaze at the stars. As the music drifted down the hill, things were not going so well for Oscar's colleague, Ian Shelton. The roof of the antiquated 10-inch telescope was jammed, and Shelton had to push it back by hand. Shelton, a young astronomer from the University of Toronto, was engaged in an off-duty project. He was taking a test photograph of the nearest galaxy to our own, a patch of faint stars called the Large Magellanic Cloud. To make just a single exposure, he would have to guide the telescope continuously for 3 hours. "2 a.m., back at the 40-inch telescope, Oscar Duhalde decided to take a break. Now, the Large Magellanic Cloud attracted his attention too.
The first thing that I noticed is that the sky was so beautiful and impressed me how transparent it was. The Magellanic Cloud looks real bright, so beautiful, and I saw a new object there. That was clear for me because I didn't saw it before.
When Oscar returned to the control room, the telescope needed his immediate attention. He had no time to think about what he had seen. For Ian Shelton, things had gone from bad to worse. The wind had risen. The roof of the shed had slammed shut and knocked the telescope over. By 4 a.m., Shelton had had enough for one night. To see if his plates had been ruined, he developed them before going to bed.
Well, I took the plate out of the wash, put it on the light tablet, and just checked it for quality, typical routine things that I do. And everything about the plate was great. I mean, I was really pleased. It was a nice 3-hour plate. But it became very clear that there was something unusual about the plate. Just close to where I normally check the guide star at the center, which is the plate center, you look for best quality. There was another star, fairly close to 30 Doradus, where there was no star there from the previous night. I had just done an almost identical plate the night before. Put it on the second light tablet, you compare them side by side. And it's very clear, everything on the plates were identical except for this extra star. And I think that that more or less convinced me that it had to have been real. Now, the big question is, was it still there? I put on my coat, came out, and stood right about here, just clear enough of the horizon to look up and see the LMC. And for the first time, I met the star in person, and it's quite spectacular.
Shelton saw what Oscar de Halde had seen, a faint patch of light in a galaxy 170,000 light-years away. He was beginning to realize that he was seeing a supernova, the rare sight of a star blowing itself apart. He rushed to tell Oscar.
That moment I remember saying, oh yes, I saw it at 2 o'clock in the morning. It's near Ceridorado. Shelton said, yes, it's okay, it's some minutes of Ceridorado. Yes, I saw it, it's very bright. And that object is new. I saw it.
The astronomers could barely believe what they had found. Supernovae play a central role in the evolution of the universe. Their explosions create the basic elements of life. Their shock waves may trigger the birth of new stars, and perhaps the formation of solar systems like our own. But a nearby supernova has not been seen since Tycho Brahe's in 1572 and Johannes Kepler's in 1604. Suddenly, Sheldon and Duhalde had to act fast. They had to telex the news to the United States, both to alert other astronomers and to claim credit for the discovery. Shelton had no idea how such a telex was sent. He had to look it up in a popular astronomy magazine called Sky and Telescope.
Digging up the reference number in terms of what volume and what page and so on, pulled out the appropriate volume, and sure enough, there's a big article called How to Send an Astronomical Telegram.
It was daybreak before the news was dispatched to the Las Campanas office in La Serena, 150 miles away. There, Bill Kunkel, the scientist in charge, faced a dilemma. The public telegraph was unreliable. He had to find a telex machine he could trust.
So the next question is, how do we get this message out? I look at my watch, and the watch says, oh God, it's 10:15. If it's 10:15 in the morning here, it's nighttime in New Zealand, and in New Zealand, they're seeing it. Huh? So you really got to hustle. And so we said, okay, take the whole thing and carry it over to the one machine that I know will respond immediately. So I say, Sonia, I've got this crazy telegram you've got to send, and I want to see it go into the machine, and I want to say the machine say, yes, I've got it. So I carry the telegram over there, and she looks at it, and she puts it in the machine, and off we go. And it went.
Shelton and Duhalde had officially registered their discovery. The word was out, and the greatest adventure in modern astronomy was about to begin. Veteran supernova theorist Sterling Colgate.
Well, see, supernova, there's what? One every second in our universe. And what's so great about that? Well, they're the biggest explosion in the universe, the biggest event, short of the production of the universe itself. When a star explodes, you know, it goes through all this nuclear synthesis, makes all the elements and all the material from which we on this planet are put together. And so every time there's a supernova in the universe, it's making all the elements that could make other solar systems and other stars like ours. And I just think it's terribly important to understand this great and fundamental mechanism that goes on in our universe.
So great is Colgate's curiosity about supernovae that he has constructed a unique telescope. One built entirely from spare parts. linked to a computer in Socorro, New Mexico. It is designed to conduct an automatic continuous search for supernovae.
Okay, that's where Socorro is, where the Eric and all the controls are, and there's a microwave link down here that transmits the computer signals to the telescope at roughly a megabaud. And now you can see the telescope is actually slewing. It's in a simulated galaxy search, and every 20 seconds we'll see it slew to a new galaxy. And then just there it's slewing to a new galaxy, and it'll be taking a picture if it were nighttime. That picture in turn goes back down to the campus, is analyzed by the computer real time. Meanwhile, the telescope is slewing to a new position, and we repeat that process time after time to try and find a supernova, try and find a star that's different in one of those galaxies.
An extraordinary intuitive physicist, Colgate was the chief test scientist for the hydrogen bomb program at the early age of 27. Then in the 1960s, he became fascinated by still larger explosions, exploding stars.
I want to know why the dang things blew up, and then why they kept on shining, and then really more than that, I want to understand how they blew up. In other words, once you know the mechanism, what was the distribution of matter when they blew up? And the first problem was that, you know, when we put in the thermonuclear fuel, that is, mocked it up in a computer calculation, we'd get a big explosion inside, but, you know, then it would go out of ways and fall back in again. It would always collapse. And it was the biggest puzzle to figure out how in the world you could get these things, as we saw them in the universe, regularly explode, and yet the calculation showed they collapsed. The exciting thing about this supernova down in the Magellanic Cloud is that we may be able to tie down all of these things, how it explodes, how it shines afterwards.
It has taken Colgate and others over 20 years to construct computer models that could mimic a supernova, models based on distant exploding stars and the remnants of nearby supernovae, which blew up in the distant past. This is the Crab Nebula, which exploded in 1054. Its expanding shell is now 60,000 billion miles across. Today, a detailed theory of supernovae has emerged, a theory that begins with the question, what kind of star blows up? Theorist Stan Woosley.
Well, it takes a large one to begin with. The sun will never become a supernova. It takes something at least 8 times the mass of the sun. The massive star has a much shorter life than the sun does because it spends its energy so much more rapidly. Its luminosity is, even before it becomes a supernova, is already very great. And so the star that we're thinking of here probably lived about 10 million years total, whereas the sun will live for 10 billion years. During its life, it does the things that stars do. It burns hydrogen into helium, and then helium into carbon and oxygen. And then because it's a massive star, it can go on to these interesting later stages where it actually burns the carbon and oxygen to still heavier elements, silicon, sulfur, argon, calcium, finally to iron. In this universe, you come to a point, however, where you can get no more energy out of nuclear fusion.
By this time, the star's life is almost over. Its interior is segregated into layers where successive elements are burning, each producing less energy than the last. At the heart of the star, an iron core begins to grow as the process of nuclear fusion can go no further. Now gravity takes over. The core suddenly collapses, producing temperatures and pressures found nowhere else in the universe. A shock wave is born, and a gargantuan burst of atomic particles called neutrinos is released.
This whole process is very fast, I should say. The time from the instability to the time you get to nuclear density is only 0.2 of a second. The stars live 10 million years, and now the time scale has obviously become very short. The shock wave goes out through the star in about 20 milliseconds. If it doesn't succeed in exploding the star, then something else will have to work, and people have been calling upon the large flux of neutrinos, which is produced in the collapse, to aid the shock in blowing apart the star. It is, even for an astronomer, it's an incredible amount of energy. It's 10 to the 53 ergs. What does that mean? It's all of the energy that the sun will give out in its 10 billion year lifetime, multiplied by 100, released in a second. It's the energy that the entire observable universe, our galaxy, all of the stars in it, all of the other galaxies, out to the edge of the observable universe, it's the energy that puts out in 1 second. It's just an incredible amount of energy. It's the most energetic phenomena that we know of this side of the very, very early seconds of the Big Bang.
Until now, the theory has been just that, a theory. Supernova 1987A would put the theory to the test. In the southern hemisphere, every instrument was turned toward it. In an unprecedented international collaboration, observers in Chile, Australia, and South Africa collected data, while theorists the world over tried to figure out what it all meant. Speed was essential. Most supernovae brighten rapidly, then slowly fade from sight. Confusions arose and mistakes were made, but the next few months would be among the most exhilarating in the history of astronomy. To begin testing their theories, scientists first had to learn which star blew up. What were its characteristics, its size, age, and color? At Siding Spring in Australia, the hunt was led by Graham White.
This is the 3.9 metre Anglo-Australian telescope. One of the principal reasons for building this telescope was to examine in detail the Magellanic Clouds which pass very high over our southern sky. When we heard that a supernova had gone off near the 30 Doradus Nebula, of immediate interest to us was to see if we could identify which star was the progenitor of the supernova. So we went to our plate library and we found that we had several plates of this region.
White hoped that one of the old plates held the key, a star positioned exactly where the supernova had appeared. He was in luck. Out of the billions of stars in the large Magellanic Cloud, he found what he was looking for. Exactly where the supernova had exploded, there was an insignificant 12th magnitude star. Its name was Sandulic -69202.
The difference in position between the supernova position and the Sanduliac star, the brightest component, star 1, was 5/100ths of an arc second, which is about 2% of the diameter of one of these small star images that you see on the screen.
Graham White's measurements clearly pointed to Sandulic as the progenitor star, but the matter was far from settled. In the United States, researchers were about to arrive at the opposite conclusion. Bob Kirshner from Harvard University was in an ideal place to learn of the supernova. His office is just down the hall from the International Astronomical Union's headquarters, where Ian Shelton's telex had been sent. Ironically, Kirshner was one of the last to hear.
Yeah, well, the phone rang, and it was Craig Wheeler from Texas calling. One of his graduate students had gone up to Toronto and had gotten the word even faster than IAU circulars. So I heard from Craig, and I immediately ran down the hall to Brian Marsden's office to see what the story was. And when I got in there, it was a scene of, well, not confusion, but action. There was, the phone was ringing, his computer terminal was going, and the teletype was making a racket as he was getting reports from all over the world about this supernova in the Large Magellanic Cloud. So I immediately ran back to my own office to call the IUE to see if we could get started on the ultraviolet observations. And literally as I was reaching for the phone, they called me.
Initially, Kirshner was less interested in the progenitor star than in the supernova itself. He wanted to observe its ultraviolet light using a satellite controlled from NASA Goddard in Maryland. The first task was to find the supernova.
This will take about a minute to position the telescope so the supernova is positioned in the center of the aperture to start our first exposure.
Right, the light from the supernova has to go down into the instrument that spreads it out and makes the ultraviolet spectrum, so that's the first step.
In the immediate aftermath of the explosion, the expanding debris of the supernova was immensely hot, and like all very hot objects, it radiated ultraviolet light. As it began to cool, the ultraviolet part of its spectrum would decline.
In just a minute, we should be seeing our first exposure today. Let's see here. Oops, return. There we go.
That is exactly what the satellite revealed.
We've been working on it every day, of course, and the thing we want to do is make sure we look at the changes and try to understand how the temperatures and how the velocities and how the composition in the atmosphere have changed over these early days. It certainly has changed a lot. The ultraviolet has gone down very steeply as the atmosphere has expanded and cooled.
As the ultraviolet glare faded, the satellite revealed a new signal. Hidden in the spectrum was the light from two stars. Because of its position, Kirshner concluded that one of them must still be Sandulik. So which star had become the supernova?
Well, we don't know which star blew up. We really don't, we're going to have to puzzle that out later. It's obviously not, or it's probably not a star with a tremendous amount of ultraviolet light, otherwise it would add into this image. But I think we're going to have to wait for the supernova to fade away and then take a nose count and see which stars are still present in the vicinity of the explosion.
Astronomers were now presented with two pieces of contradictory evidence. Graham-White's, which showed that Sandulik had blown up, and Bob Kirshner's, which showed that Sandulik was still there. The mystery was solved in Baltimore at the Space Telescope Science Institute.
Okay, I'm going to erase the screen now and bring up one of our fine scanned regions of the Sandulik 202 object.
Okay, get right.
Barry Lasker and Nolan Walburn followed the same path as Graham-White and began their search for the progenitor star by examining old plates of the large Magellanic Cloud.
Okay, there it is. Let me give you a full screen display of it.
By feeding these images into a computer, they were able to examine the Sandulik star in greater detail. When examined close up, a subtle new feature emerged.
Quite obviously, there's a fainter companion to the principal star to the northwest, who's now called Star 2. But on closer inspection, we could also see that there's a bulge or an asymmetry almost directly opposite to that. And the hypothesis was that there was a third star in the system, which is now called Star 3, in that position.
But was the third star real, or was it an artifact of the photographic process?
Let's just re-display this image in pseudocolor because I think that makes it a little bit easier for the eye to follow. And notice that the elongation is not along this axis, which it would be if you were dealing with a simple photographic or psychological effect, but rather the elongation is like that. It's in an orientation that is not defined by the rest of the system. The conversation from there went, okay, how do we convince anybody else of the reality of this?
Lasker and Walburn performed an ingenious maneuver. First, they selected a single star roughly similar to Sandulik. Then, superimposing the images, they subtracted one from the other. With Sandulik removed, the presence of a third star at the lower left was clear. They had found the missing piece of the puzzle. Originally, there had been 3 stars. When the supernova exploded, 2 remained. It was the light from these two stars, not Sandulik, that Bob Kirshner had seen.
We really came to believe that the interpretation was simple, the astrometry was correct, Sandulik 202 was the progenitor.
The progenitor star was confirmed, but now a part of the theory did not fit. Sandulik was a blue star, a star too young and too compact to explode. Theory predicted that only giant red stars become supernovae. If this primary assumption was in error, was it possible that other parts of the theory were wrong? A crucial test would come next as scientists scrutinized the debris ejected by the supernova's monumental blast. The theory was clear about what should be seen.
Well, we see what we see in any explosion, the expanding debris of 10 to the 20 megatons. We see first the skin, the surface of the star, because the star is very opaque. Just like when we look at the sun, we see its photosphere, its outer edge. And that as that expands and gets thinner, we can see deeper and deeper into the star. And so we see revealed, like layers of an onion, the shells of all of these nuclear burning stages that have gone before. After we're through the hydrogen, we're into the helium, and then into the carbon and oxygen, and ultimately to the beast that was made during the collapse, the neutron star that is in the middle now.
A neutron star is one of nature's most bizarre creations, an object the size of the sun, shrunk by gravity until it is a mere 12 miles in diameter. A star so dense, it weighs 10 billion tons per cubic inch. When a neutron star is born, even the space within atoms is squeezed out. Electrons and protons fuse to form neutrons. Huge amounts of energy are released in a burst of subatomic particles called neutrinos. Some contribute to the star's explosion, but, claims the theory, most stream off into space to reach the Earth even before the brightening of the supernova is visible.
99% of the energy, which comes from the binding energy of the neutron star which is made, comes out in the form of neutrinos. Only 1% of this energy goes into exploding the rest of the star, and then 1% again, so a hundredth of a percent of the total energy comes out in the light that we see. So bright as it may be, a supernova optical display is only incidental to the really true major explosive event, which is the neutrino emission.
Did the supernova emit neutrinos as the theory predicts? The best chance of finding them was to come from an experiment buried deep in a zinc mine at Kamioka in western Japan, run by Yatsuo Totsuka and his American collaborator, Al Mann.
We are going to the deepest part of the mine, where it will take about 15 minutes to ride. Then we will leave the train and walk for about 5 to 7 minutes to the experimental area. The only way to survive this ride is to close one's eyes and one's ears and communicate with your inner self.
By working underground, the scientists can screen out cosmic rays and other particles which would interfere with the experiment. Neutrinos can streak straight through the millions of tons of rock. The detector itself is a giant tank of water 4 stories high, embedded in the mountain. Since the supernova is in the southern hemisphere, neutrinos arriving here would have passed through most of the Earth and be heading out again into space. If a neutrino enters the tank, it may collide with an electron in the water. The electron is accelerated until it gives off a bow wave of what is called Cherenkov radiation, which can be detected as a circle of blue light at the edge of the tank.
We are now on top of our detector, our cylindrical tank. And this blue metal plate seals the top of the tank completely. And below that, we have 3,000 tons of pure water. And on the whole inner surface of the tank, we have 948 foot multipliers.
These photomultipliers are unique in the world. To have such large diameter photomultipliers enables us to cover 20% of the surface of this tank, top, sides, and bottom.
The huge photomultiplier tubes, the inspiration of the tank's designer, Professor Koshiba, make it the most sensitive neutrino detector yet built. 2,000 wires feed signals to a computer in the control room outside, which continuously records the results on magnetic tape. When the supernova exploded, the tapes for February 23rd were hurriedly shipped to Tokyo University. Almost a day before Ian Shelton saw the supernova, a sharp spike had been recorded. Of the billions of neutrinos passing through the tank, just 11 were detected. Even before they checked the results, the experimenters could scarcely conceal their delight.
I think, what should I say? Well, we were terribly excited about this. I mean, we went to the display and looked, and you clearly see a circular Cherenkov pattern here, with some light scattered away from the Cherenkov ring. We believe that this is the most beautiful events we observed.
Seen here in 3D, the ring of light, and 10 more like it, prove that neutrinos passed through the tank. It was a historic moment, confirmation that when supernovae collapse, they become neutron stars.
At that time, we were cheering and we got excited. Anyway, this is really the first observation of the neutrinos outside solar system.
While the experimenters were pleased, the theorists were ecstatic.
I was just far out, man. When I heard when I heard from the supernova that there were neutrinos, and that this, this theory of so many years in a lifetime was suddenly out there, oh my God, what a trip, man. What a real trip. It was just, these neutrinos, oh, can't do any more.
After 40 years in the business, Al Mann is more circumspect. He knows how much discoveries in science depend on luck.
The whole event, as far as the neutrinos are concerned, only lasts 13 seconds, approximately. And during every hour, we turn off our data taking in order to calibrate the system for 105 seconds. And so we were off a few minutes after the supernova neutrinos arrived at us. We were off 2 minutes later for 105 seconds. And if we had been slightly less lucky, we would have missed the event entirely.
The detection of neutrinos was a triumph. For the first time, scientists could claim to understand the complex events 170,000 light years away in the heart of an exploding star.
And the marvelous thing now is that we have a chance to make some real observations.
2 months later in Washington, D.C., a distinguished group of physicists gathered to celebrate the success.
The fact that we can understand is just absolutely out of sight. I mean, the notion that we can really understand these things, I can't believe it, because, damn it, this whole house of cards gets built up,
Present were Sterling Colgate, Nobel Prize winner Willie Fowler, and Fred Reines, whose American-based collaboration also detected neutrinos from the supernova.
We have a chance to actually do some experimental observational work and check up on all the theories that these young guys are...
Wait till we get one in this galaxy, though. I can taste it. I can just taste
this
it.
is close enough for me.
No, you just see that dang, those neutrinos go ka-chunk, ka-chunk, ka-chunk.
Neutrinos were not the sole topic of conversation. There were rumors that Bob Kirshner had finally changed his mind about the progenitor star.
About 100 more.
No, I think Kirshner's kind of caved on Sandelook, really.
Well, now, I've heard all kinds of argument about this. You're saying that the original statement that it was this particular star.
It was retracted.
Was retracted, and now it's back.
And now it's back again.
But Kirshner also thinks that. I mean, he says it is gone, and that he likes it to be minus 69,202.
Say again?
Kirshner agrees with you. I think he's going to say that tonight.
Yeah.
Give me enough rope.
Well, it's a great pleasure to see so many familiar and especially to see so many unfamiliar faces. That is to say, I think that the observations that we've seen over the last month of this very interesting object have brought together a very wide group of people who ordinarily pass one another in halls with polite grunts at best. Supernova 1987A has some special features. I think all of those special features, or most of them, can be accounted for by the hypothesis that the supernova really did come from the Sandulik minus 69,202 star, that it's the one that blew up. It's massive, so it would we expect to form a neutron star. So I think, and most importantly, down in red, the star is now absent. So it seems to me, that in a positive sense, this would have all the right characteristics, and the fact that it's not there makes it a plausible case, I think, that the Sandulik star is the one that blew up and became the supernova 1987A.
But was Sandulik a new kind of supernova? According to theory, blue stars do not explode. As evidence from Siding Spring in Australia revealed, the supernova had behaved unusually from the start. The first hint that it might be different was found by Rob McNaught in a single critical photograph. McNaught is a young Scotsman who works for the University of Aston in England. Professionally, he is employed to take photographs of Earth-orbiting satellites using an ancient Schmidt telescope, a sort of giant camera. But in his spare time, he is an enthusiastic amateur astronomer who photographs the sky, searching for unusual stars almost every night. On February 23rd, 4 hours before Ian Shelton began his exposure, McNaught photographed the large Magellanic Cloud. Then he made a fateful mistake. After developing the film, McNaught drove home and without inspecting his photographs, went straight to bed.
After a couple of hours, I had a really horrible nightmare, which is something really unusual. I haven't had a nightmare for some years, which, whether or not that's significant, I wouldn't want to say, but after a couple of hours, I woke up. It was still dark. The sky was still cloudy, and I took the film down, cut the individual slides up, mounted them, and thought about possibly searching them to see if there were any nova in the Large Magellanic Cloud. But for some reason, which I'll never understand, I didn't search them then, or several other times during the day when I thought I should have a check to see.
Not until news of the supernova arrived did McNaught check his photographs. Here was the very first picture of the exploding star.
Perhaps the unfortunate thing was, although it would have been nice to have made an early discovery, more important would have been to have had the discovery reported earlier, so that spectra could have been taken in the early stages when obviously very unusual things were happening.
McNaught's photograph, taken within 3 hours of the neutrino's arrival, was of great value. It showed that Sandulik had brightened within hours of the initial explosion. Previous supernovae had followed a regular pattern. For several weeks, they grew in brilliance before reaching a peak. McNaught's photograph proved the new supernova had brightened enormously in just 3 hours. Then it suddenly stopped brightening. Its light leveled off while it was still 10 times dimmer than expected. This peculiar behavior, it turned out, could be explained by Sandulik being a blue star.
The supernova seemed to evolve very rapidly in the first few days. It got up onto its plateau in just a few days, whereas that usually takes a much longer period of time. And furthermore, it was fainter by about 2 magnitudes than one would expect for type 2 supernovae, at least the ones we've seen in the past. These problems are all really related to the fact that it was a blue supergiant that exploded and not a red one.
Red supergiants are stars 10 to 100,000 times brighter than the sun, with diameters so large they would stretch beyond the orbit of Mars. As a blue supergiant, Sandulik was equally bright, but only 1/10 the diameter. Because it was much denser, it took more energy to expand and less energy remained to appear as light.
If you start with a more compact star, it must expand to about the same distance as a red star would have before you can begin to see the radiation get out. But because it has further to go, starting from a smaller radius, it loses more energy in the expansion process and so appears fainter. So the fact that it was fainter on the plateau is related to the fact that it was a blue star. Also, the fact that it evolves so quickly, the velocities are higher when you start with a more compact star, and you end up getting onto the plateau stage quicker, so the whole evolution is accelerated.
The explosion had blown debris into space at an astonishing 50 million miles per hour. But to even the most powerful telescopes, it was no more than a pinpoint of light. What did the exploding star look like? To answer that question, observers began to train more exotic instruments on the supernova. This is the NASA Deep Space Station at Tidbinbilla near Canberra in Australia. Using these giant radio telescopes, astronomers hoped to see the supernova's expanding shell. Yet the sudden appearance of the supernova caught the Australian radio astronomers off balance, as David Jauncey admits.
Well, look, the first news came through was at Telex in Sydney. I was up in Sydney at the time, and the word just went around very quietly amongst a few people that there was a supernova in the large cloud. And I think everybody's initial reaction was, okay, there's a supernova in the large cloud. But within half an hour, I think the penny dropped, and it was, there's a supernova in the large cloud. So there was just a lot of running around. I mean, people were preparing, thinking of what they might do. It's something that we've had 400 years to think about, but it's not the thing that you're ready to say what you want to do. And I think the initial reaction really was, indeed, what can we do?
Because of their size, radio telescopes can reveal greater detail than their optical counterparts. This is Tycho Brahe's supernova of 1572. And this is Cassiopeia A, which exploded about 300 years ago. David Jauncey and his colleagues planned a bold experiment.
Okay, there's Cyril. You've got the antenna?
Yes, and the macros loaded.
Okay, well, we can get onto the supernova as soon as John comes in with those coordinates.
They would link radio dishes in Australia with a dish in South Africa. The resulting telescope would be, in effect, 5,000 miles in diameter. But coordinating this kind of operation is tricky. Recordings made at the distant sites would later be recombined in the United States. To generate images, the supernova would have to be neither too small nor too large for the telescope to see.
Okay, 45x 4F. Thanks, John. Okie doke.
For the system to work at all, the different telescopes had to record the supernova at precisely the same radio frequencies.
P sub A equals minus 69, 16, 50. And the right ascension is 05, 35.1. There we are, on our way.
It was a heroic undertaking, but in the rush to get ready, the observers almost slipped up.
I mean, all the tapes went off and we sat around and breathed a sigh of relief and sent all of our logs back to the States, back to Bob Preston. And Bob sat down and did the calculations and said, you know, you've stuffed it up, you're 2 megahertz off. I'm laughing now, I wasn't laughing then. Went home, this was a couple of days, actually about a week later, went home and really felt bad. I mean, you know, with the optical telescopes, if they miss it in Chile, they'll catch it in Australia. If they miss it in Australia, they'll catch it somewhere else. But with the radio telescopes, because we really are the only facilities to do this, the only place on Earth that can do it, it really felt bad. You know, one opportunity in 400 years and we'd blown it. So I don't know about the others. I spent a very disturbed night until I realized about 4 o'clock in the morning that in fact what we really had done, because it was exactly the width of one recording channel, that instead of having them all line up like this, what really had happened is we just slipped them all down one. So in fact the data was, with some modifications at the correlator in the States, the data was totally recoverable. And at that stage, I guess from about 4 o'clock in the morning, I slept one of the best sleeps I've had for quite a long time, at least for 4 hours until the phone rang again.
Ironically, the supernova had grown so fast, it was already too large for the telescope to see. It was like trying to read a book through binoculars. Then, the initial burst of radio signals disappeared. As the supernova continues to expand, the dust and gas surrounding it will thin, and in the coming months, the signals should reappear. Using a smaller array, David Jauncey will try again.
At present, all we have is silence. So what we're doing is monitoring it 3-4 times a week. Here, they're doing the same thing at Molonglo, and we're just waiting. I think we have the opportunity now with the VLBI array, when the source comes back again, to actually map it, to get a picture of it, a radio picture of it, and watch it as it expands. So we're all ready with a lot of effort from here and from the United States and in fact all around the world. We're ready and waiting. We just hope that our theories are right, because a lot of effort's gone into getting ready for it. If the theories are wrong, then we wait indeed for nothing.
Despite the radio astronomers' bad luck, by mid-May, observing the supernova had become routine. With minor adjustments to the theory, most of its behavior could be explained. Then came a baffling new discovery. It was made at Cerro Tololo Inter-American Observatory in Chile, 100 miles south of where the supernova was discovered. In early March, 2 scientists from Harvard University had arrived to carry out an intricate experiment. Kostas Papaliolias and Peter Niesenson are experts in a technique called speckle interferometry. Using it, they too hope to see the supernova shell as it continued to expand. Speckle works by taking thousands of brief images of an object. When combined by a computer, the distortions produced by the Earth's atmosphere can be evened out. Each dot is a single photon of light from the supernova. 2 months later, at the end of May, Peter Niesenson returned to Tololo with an astonishing announcement.
When we looked at the field around the supernova, we found another bright source, a source that is only about 3 magnitudes fainter, that's a factor of 10 fainter than the supernova itself.
Can you show us the evidence for that?
Yeah, I've got some pictures, and these are some results that came out of our processing of the data from last time. As soon as we saw this come up on the screen, we saw something that was what is normally characteristic of a double star, which is that you see dark lines and bright regions that are essentially linear in direction. And they're quite coarse, which means that the separation of the two sources is pretty close. And finally, we've got a reconstructed image where we actually see the source in the position that it actually is.
The faint new object to the left is actually 100 times brighter than Sandulek or any other nearby stars. Clearly, it is related to the supernova, but what could it be?
A lot of people have come up with a lot of exotic theories, but nobody has anything definitive. Everything from black holes to other supernovas to other things. We can't say at this point, but that's really what this next run is all about.
Throughout August, the observers continued to argue about whether the new object was still there.
They're going to try to find a star that's closer.
Is there a hole in the supernova's shell where light from the neutron star leaked out? Or was a piece of the neutron star itself blown into space? Time will tell. And while the observers watch, the theorists try to predict what else the coming year will bring.
Now, the most exciting prediction is the one that's most difficult to make, and that is, what are we going to see of this monster that lies in the middle? We've predicted that it's a neutron star. It's not massive enough to be a black hole. We predict its mass is 1.3 solar masses. But most interesting is going to be how it appears. Is it rotating rapidly enough to be a bright pulsar? Does it have a strong magnetic field? If so, then about a year from now, we should see some very dramatic effects of a rapidly spinning magnetic neutron star down in the middle of this thing. It may come in the form of pulsed emission. It may come in the form of X-rays and gamma rays besides those produced by radioactivity. But something is going to come, and it's going to be exciting. That's a prediction.
Ladies and gentlemen, here, supernova Shelton.
The supernova has touched the life of every scientist who has studied it, none more than its discoverer, Ian Shelton. Summoned home, he told his story to his colleagues and to his family.
Las Campanas being the wonderful place it is, I always wanted to be there, and I'm glad I had the opportunity to get down there. The first time, thanks to Bob for taking a chance, and I guess 2 years ago, he took another chance on me and let me go back for a return engagement, I guess. And I guess I did good.
Whatever the supernova does next, Ian Shelton's place in history is secure. But perhaps that is less important than the thrill of making the discovery itself.
Great to have been in on the bottom floor. It's great to be here when it was first seen. And I think I've done substantial as far as following it up for the last 3 months. It's been great. But I don't think anything's ever going to replace that night of actually seeing it for the first time. That was memorable.
Oscar de Halde will not quickly forget the past few months either.
Well, I think it's a privilege that the life give me thinking in this. I was the first official person that saw the supernova between the world population, about some billion of people. And it was a privilege to stay in the right moment because the light take about 170,000 years to arrive to the Earth. And I was here in this mountain at the right time, in the right place for see it. I think that is a really life privilege. It's the only explanation for me.
fuggevolo ora s'innebbia voluta, li bionde volgi fremiti che suscita l'amore, poiché quell'occhio al cuore ogni